let's just take a look at some of the properties of straightness. For example, if you take a tangent to a straight line at any point, of course it's a straight line, right? And then you push it up along itself, right? Take like the last half of the tangent and move it up alongside itself in a parallel way, transporting it up to the top. And then take the rest of it and transport it parallel to itself again up to here, and up to here, and up to here. You eventually, of course, will get a long straight line. In other words, the first initial segment, or any segment for that matter, transported in a parallel way to itself, then recreates the entire length of the line. This is, in fact, a property of geodesics. Of course, in a weird kind of space, it's not going to be so simple to define what you mean by transporting something parallel. But there are mathematically precise ways of defining that. And then you get what you would call the straightest possible line in that sophisticated space. In a straight line, we know not only that it's straight individually at each point, it's straight overall. We know the whole shape is specified by any initial piece or any tangent piece. And we're going to look a little bit later at candidates for geodesics according to these criteria. The initial tangent completely determines the shape of a straight line, where the initial tangent, or any tangent, tells you exactly where it's going to go. It gives you the overall shape and etc. So now let's get back to geometry and straightness and so on. If we want to talk about straightness, so we see that a gravitational trajectory will be a straight line in a free fall frame. What other properties that seem like geodesics would a gravitational trajectory have? Okay, again, I'll just pose this question and see if you can think of something. So now, let's get back to geometry and straightness and so on. If we want to talk about straightness, so we see that a gravitational trajectory will be a straight line in a free fall frame. What other properties that seem like geodesics would a gravitational trajectory have? Okay, again, I'll just pose this question and see if you can think of something. I'm looking at several things. One, that how to characterize the shape of a trajectory. And what I'll do is I'll characterize it by, if this is y max, that divided by the extent on the x-axis, y over x. So the question is, what determines that shape? And whether that shape is unique, so that if I've just given those two things, I can uniquely reconstruct the trajectory, or there are many trajectories that could have that height with that extent. Can I draw this line, or are there several different ones?
Okay, so same height with, and same distance basically.
Same height and same distance. Can there be more than one?
Could be more than one.
And what does that turn out? What does that ratio turn out to be? Y max over x, or delta x that it went.
In terms of velocity.
In terms, right.
Okay. Assuming constant gravity.
Right. You can assume g is a whatever. Just
constant. Okay.
all right, so far I see that you have it, right? A quarter y over vox, right?
Okay.
Yeah. Okay. Basically, I'll give you. You can solve this. It's a very, very nice little problem. You just get something very, very simple. A quarter voy over vox. So it's the ratio of voy over vox that determines it. And what is the trajectory? What is the initial angle of the trajectory? What determines that?
Tan inverse Vy over Vx.
Right. Just
Oh, okay.
Vy over Vx. In other words, the angle at which you throw it, one might almost tend to think that you can arbitrarily determine the angle that you're throwing it and what velocity you're going to throw it at, so to speak. You can, but whatever velocity you throw it, it's going to have a unique decomposition in terms of cosine and sine of it. You can't choose to have a very, very great Vox and a very small Voy and also throw it at whatever angle you choose. By definition, the velocity is in a certain angle, and that decomposes. All right, so VOY over VOX determines the angle of the trajectory, even though it's a trajectory diagram rather than like velocities. The tangent of the trajectory is not the velocity, but the tangent, the initial tangent of the trajectory is specified by the ratio of the velocities. Okay? Now, since this ratio is determined by VOY over VOX, if you solve it, you'll find that. Therefore, it's totally determined by, this ratio is totally determined by the angle, the initial angle of the trajectory. In other words, given an initial angle of trajectory, you have a unique ratio of this to that. Okay? And in fact, there's only one such trajectory. So, and also, any particle, whatever mass you throw, with that initial angle, right, is going to have that ratio. Now, depending on what the absolute value of VOX and VOY, the ratio will determine this. Of course, if it's a bigger amount, it'll be a bigger trajectory. It'll have the same shape, like nested shapes for a smaller absolute amount, same ratio, bigger, same ratio, but larger absolute, and so on. So it uniquely determines the shape. So here we have something very intriguing and nice. The initial tangent of the trajectory completely determines the shape of the trajectory. It doesn't determine, though, where it's actually going to go, because given this tangent, it could go like this, like that, whatever. So it selects out a very particular family of curves, but not uniquely. So it's something like a geodesic. It's something like a straight line where the initial tangent or any tangent tells you exactly where it's going to go. It gives you the overall shape and etc. This does give you the overall shape, just not the scale. If you know just the angle, all you know is the ratio of the speeds. You just know the general shape.